Hello friends, good afternoon everyone. I am fine. How are you? I hope you will be fine. Welcome back in my channel Dr.Satendra Kumar. Dear friends, if you want this type of videos related to mathematics for higher level, then you need to subscribe, share and like my videos and my channel. Today we will discuss the expansion of the function by Taylor series theorem and Lorentz series theorem. Now, first question number first. So that z modulus lesser 4 greater 0 1 upon 4z minus z square equal summation n is equal to 0 to infinity z to the power n minus 1 upon 4 to the power n plus 1. Okay. Now answer. Fz equal 1 upon 4z minus z square. Now we take common 4z, 1 minus z by 4 whole power minus 1, expand binomially 1 upon 4z, 1 plus z by 4 plus z square upon 4 square plus up to dot. This is equal z to the power minus 1 upon 4 plus 1 upon 4 square plus z upon 4 cube plus z square upon 4 to the power 4 plus up to dot. This is equal to summation n is equal to 0 to infinity z to the power n minus 1 upon 4 to the power n plus 1. Okay student? Now next question number 2. Prove that 1 plus 2z upon z square plus z cube equal 1 upon z square plus 1 upon z minus 1 plus z minus z square plus z cube minus up to dot dot. When z modulus greater than 0 less than 1. Okay. Take fz equal 1 plus 2z upon z square plus z to the power 3. This is equal to 1 plus 2z, z square is common, 1 plus z on partial fraction 1 upon z plus 1 upon z square minus 1 upon 1 plus z. That is fz 1 upon z square plus 1 upon z minus 1 plus z whole power minus 1. This is equal to 1 upon z square plus 1 upon z minus 1 minus z plus z square minus z cube plus up to dot. This is equal to 1 upon z square plus 1 upon z minus 1 plus z minus z square plus z cube minus up to dot. That is fz is expanded by, that is fz is expanded by Lorentz series. Lorentz series in this annulus. Now next question, question number 3. Expand 1 upon z square minus 3z plus 2 for the region number first, z modulus greater than 0 less than 1. Number second, z modulus greater than 1 less than 2. Number third, z modulus greater than 2. Answer: since fz equal 1 upon z square minus 3z plus 2, this is equal to 1 upon z. Factorize this: z minus 1, z minus 2 by partial fraction. Fz equal 1 upon 2z minus 1 upon z minus 1 plus 1 upon 2z minus 2 in first region. Z modulus greater than 0 less than 1, that is fz equal 1 upon 2z as it plus 1 minus z whole power minus 1. Since 1 is greater than 0, 1 is greater than z, therefore 2 is also greater than z. Now minus 2 common, minus 1 upon 4, 1 minus z by 2 whole power minus 1. This is equal to 1 upon 2z plus 1 plus z square plus z cube plus up to dot minus 1 upon 4, 1 plus z by 2 minus plus z square upon 2 square plus z cube upon 2 cube plus up to dot bracket close. This is equal to 1 upon 2z plus summation n is equal to 0 to infinity z to the power n minus 1 upon 4 summation n is equal to 0 to infinity z by 2 whole power n. Okay, that is which is the required Laurent series, which is the Laurent series expansion. Now second part, z modulus greater than 1 less than 2. In this case, fz equal 1 upon 2z as it. In fz 1 upon 2z as it. Z is greater than 1. Now z is common, 1 upon z, 1 minus 1 upon z whole power minus 1. Therefore z is common, plus 1 upon 2z, 1 minus 2 upon z whole power minus 1. This is equal to 1 upon 2z minus 1 upon z, expand binomially 1 plus 1 upon z plus 1 upon z square plus 1 upon z cube plus up to dot plus 1 upon 2z, 1 plus 2 by z plus 2 square z square plus 2 cube z cube plus up to dot 1 upon z plus 1 upon z. This is equal to 1 upon z. 1 upon 2z plus 1 upon 2z. This is equal to 1 upon z. This is cancelled by this. Okay. Minus 1 upon z square or plus 1 upon z square is also cancelled. Therefore, 2 minus 1 1 upon z cube plus 2 square minus 1 square 1 upon z to the power 4 plus 2 cube minus 1 upon z to the power 5 plus up to dot, which is the required Lorentz series expansion, which is the required Lorentz series expansion. Okay, student. Now next question number 4. Find two Lorentz series. Find two Lorentz series expansion in power of z of the function fz equal 1 upon z into 1 plus z square. Now answer. Since fz is equal to 1 upon z 1 plus z square, on partial fraction 1 upon z minus 1 z upon 1 plus z square. Partial fraction. Okay. Take the region z modulus greater than 0 less than 1. The expansion of the function can be written as 1 upon z as it minus z 1 is greater than, therefore we take common 1, then we get 1 plus z square whole power minus 1. This is equal to 1 upon z minus z, expand binomially 1 minus z square plus z to the power 4 minus z to the power 6 plus up to dot. This is equal to 1 upon z minus z summation n is equal to 0 to infinity minus 1 to the power n z square whole power n, which is the required Lorentz series expansion. Required Lorentz series expansion. Now take second region z modulus greater than 1, then fz equal to 1 upon z minus z 1 plus z square. Therefore 1 upon z as it minus, now z is greater than 1, therefore we take common z square, 1 plus 1 upon z square whole power minus 1, 1 upon z minus 1 upon z, expand binomially 1 minus 1 upon z square plus 1 upon z to the power 4 minus 1 upon z to the power 6 plus up to dot. This is equal to 1 upon z minus 1 upon z summation n is equal to 0 to infinity minus 1 to the power n 1 upon z square whole power n. Okay, which is the required Lorentz series, which is the required Lorentz series expansion. Okay. Now next question number 5. Find the Lorentz series of the function fz equal 1 upon z square into 1 minus z about z is equal to 0. Okay, since fz equal to 1 upon z square 1 minus z on partial fraction, there is no need to partial fraction because we find Laurent series expansion about z is equal to 0. Therefore 1 upon z square as it. Now 1 minus z whole power minus 1. Expand binomially 1 upon z square 1 plus z square plus 1 plus z 1 plus z square 1 plus z cube, sorry 1 plus z square plus z cube plus up to dot infinite number of terms in this series. Therefore 1 upon z square summation n is equal to 0 to infinity z to the power n. Okay, or 1 upon z square plus 1 upon z plus 1 plus z square plus z cube plus up to dot. This is equal to 1 upon z square plus 1 upon z plus 1 plus summation n is equal to 1 to infinity z to the power n. Okay, which is the required expansion? Which is the required expansion? Okay, now next question number 6. Find the expansion of expansion of 1 upon z square plus 1 z square plus 2 in the power of z when first part z modulus greater than 1, second part z modulus greater than 1 less than under root 2. This is the concentric circle annulus. Now third part z modulus greater under root 2. Okay, now solution. Let fz is equal to 1 upon z square plus 1. Now z square plus 2 on partial fraction. We get fz is equal to 1 upon z square plus 1 minus 1 upon z square plus 2. In the first region z modulus less than 1, then fz will be 1 is greater than, therefore taking the common 1 plus z square whole power minus 1. 1 is greater than z, therefore 2 will also be greater than. Now taking the common 2, 1 plus z square by 2 whole power minus 1. This is equal to 1 minus z square plus z to the power 4 minus z to the power 6 plus up to dot infinite number of terms in the expansion. Now 1 upon 2 expand binomially as well as first term. 1 minus z square upon 2 plus z to the power 4 upon 2 square minus z to the power 6 upon 2 to the power 3 plus up to dot. This is equal to summation n is equal to 0 to infinity minus 1 to the power n z whole power n whole power 2n minus 1 upon 2 summation n is equal to 0 to infinity minus 1 to the power n z square upon 2 whole power n. Okay, student? Therefore, in the expansion of the function, the power of z always positive. Therefore, we can say the expansion of the function here is Taylor series only. That is, which is the required Taylor series expansion? Which is the required Taylor series expansion. Now, when region z modulus greater than 1 less than under root 2, then fz equal to under root 2 is greater than 1. Sorry, z is greater than 1. Now z common in this fz, that is z square is common, 1 plus 1 upon z square. Here 2 common, 1 plus z square upon 2. This is equal to 1 upon z square. 1 plus 1 upon z square whole power minus 1, 1 upon 2, 1 plus z square by 2 whole power minus 1. Binomially expansion, this is equal to 1 upon z square, 1 minus 1 upon z square plus 1 upon z to the power 4 minus 1 upon z to the power 6 plus up to dot infinite number of the terms in the expansion minus 1 upon 2. Expand same by binomially theorem. 1 minus z square by 2 plus z to the power 4 upon 2 square minus z to the power 6 upon 2 to the power 3 plus up to dot. This is equal to 1 upon z square summation n is equal to 0 to infinity minus 1 to the power n 1 upon z square whole power n minus 1 upon 2 summation n is equal to 0 to infinity minus 1 to the power n z square by 2 whole power n. Okay, student? Which is the required Lorentz series expansion? Which is the required Lorentz series expansion. Now third part, when z modulus greater than under root 2 in the region, the expansion of the function can be written as fz equal to z square is common. In the fz, 1 plus 1 upon z square whole power minus 1 minus 1 upon z square plus 1 upon 2 upon z square whole power minus 1. This is equal to 1 upon z square. Expand binomially. 1 minus 1 upon z square plus 1 upon z to the power 4 minus 1 upon z to the power 6 plus up to dot minus 1 upon z square. 1 minus 2 upon z square plus 2 square upon z to the power 4 minus 2 to the power 3 z to the power 6 plus up to dot infinite number of terms in the expansion. Now the first term 1 upon z square is cancelled by the first term of the second series. Okay. Now 1 upon z square is negative, 1 upon z to the power 4 is negative, and plus 2 upon z to the power 4. That is, we can write 2 minus 1 into 1 upon z to the power 4 minus 2 square minus 1 upon z to the power 6 plus 2 to the power 3 minus 1 upon z to the power 8 minus up to dot. This is equal to summation n is equal to 1 to infinity minus 1 to the power n plus 1 2 to the power n minus 1 into 1 upon z to the power 2n plus 2. Okay, student? Which is the required Lorentz series expansion? Which is the required Lorentz series expansion? Okay.